everybody, my name is Amal Saadallah and I work as a research assistant in the Artificial Intelligence Group of TU Dortmund. Today I will present our paper entitled Active Sampling for Learning Interpretable Surrogate Machine Learning Models. I will introduce the outline of this presentation. First, I will talk about interpretability in machine learning, some definitions and state of the art. Then I will present our approach entitled ASIN, Active Sampling for Interpretable Models, and show you the results we achieved in terms of approximating black box models, some aspects of debugging and interpretation, and finish with some concluding remarks. The application of machine learning algorithms to knowledge discovery from databases is expected to transform data into meaningful knowledge that can be executed afterwards in terms of actionable decision making. However, human interpretation does not always comply with the output of machine learning algorithms as they go far beyond the technical level. Hence, it is very important to interpret machine learning models to increase the related technology acceptance level and reliability. Many definitions of interpretation have been proposed in the literature. The first definition given by Miller states that interpretability is the degree to which an observer can understand the cause of a decision. Another definition provided by Bin et al. States that interpretability is the degree to which a human can consistently predict the model is a result. A common agreement between all the works that handle interpretability is that the higher the interpretability of a model is, the easier for a human to comprehend why certain decisions have been made. Interpretability techniques can be divided into two main families. The first one relies on training interpretable models per construction, like short decision trees or sparse linear model. The second models are post hoc techniques that are applied after training black box model and then suggesting either methods for interpreting or understanding deep neural networks. The second family of methods within this type relies on surrogate modeling by training surrogate interpretable model to approximate the black box model. Staying with post hoc techniques, we may also classify them according to various criteria, either model specific that are designed for specific model classes or model agnostic that can be applied to any type of models, and they are not restricted to a particular form of interpretation. Different scopes also can be considered while providing interpretation, either global one, if we present a holistic overview of the model, is output to understand its decision, or local, where we apply global model to some subparts of the model is output. Model agnostic are considered to be more flexible, and they can be themselves divided into two main families: feature-based approaches or model-based approaches. Model-based rely on surrogate modeling that approximate black box models. Afterwards, interpretation are drawn using the interpretable model to understand and debug the black box model. They are considered to they can be learned locally or globally. However, global models have the advantages that they give more flexibility to the user seeking for interpretation, so that is not lost in the details that may render interpretability itself harder to achieve. Global surrogate model can be applied to interpreting deep learning model, approximate black box model, or either interpreting ensemble methods. Another aspect to be considered while either learning or providing interpretation with the global surrogate model is data selection. That can be done using model-specific approaches, like expanding, for example, the data that lie within the margins of support vector machine, or model agnostic, like the work that have been presented recently by Pedrisky et al., stating that it's more accurate to provide or to build an interpretable model for data that have high probability to belong to a decision boundary of a black box model. For Bastani et al., they treated data selection for the construction of the model, a global model itself, and they showed that it's very important to sample a high number of data points to learn surrogate decision tree so that they converge to the exact greedy decision tree. However, this is not always very useful in practice, since we are mainly limited by the available amount of data for training. Opposingly, we propose an active sampling approach that use a lower amount of data for training a surrogate model that has a good approximation quality. It is also based on an iterative approach that allows for interaction with the experts. Moving to the formal presentation of the problem that we want to approach, imagine that we have a training data drawn from an unknown function f that we want to approximate using a black box model G. After the training, we output the prediction of G on an independent dataset GS on which we train a surrogate interpretable model, so to understand and interpret G. Imagine also that we can draw an additional unlabeled dataset to enrich the S so that we improve the approximation quality of the surrogate model. Here the question to ask which data point we need to sample from DA. A naive way, of course, would be to consider all the data points in DA to enrich the S. However, we propose an active sampling approach that is based on the active learning paradigm that selects the most informative data points to be added for the training of the surrogate model so that we improve the approximation quality of the black box model G by S. Therefore, we start by training G on GG, then train S on the independent dataset GS and use as target prediction of G on GS, and starting within the iteration process by computing the prediction of G on the unlabeled dataset GA, compute the prediction of the surrogate model on GA, and for each data point belonging to GA, we compute the disagreement between G and the surrogate model, and select data point having the highest disagreement between both of them to be added to DS with the corresponding label, which is the output of the black box model. We retrain S on the updated DS, and then we remove the selected data point from GA. After finishing with this iterative process, we measure how well S approximates the black box model G, and we use it to understand G. Two main questions here are to be raised: which selection criteria to be considered, and when should we stop the iterative process? For the selection criteria, it's an interaction between the black box and the surrogate model that should translate a kind of disagreement between of them, and we use the variance between the output of the black box model and the surrogate model for each sample belonging to DA, and points with the highest disagreement are selected. For the stopping criteria, two conditions are to be monitored: the maximum number of iterations that translates the maximum budget that the user wants to spend on this iterative process in terms of time and resources. Since we want to improve the approximation quality of the surrogate model, this should not be done at the expense of complexity, since we are looking for interpretation. That's why we suggest also to monitor the complexity of the surrogate model obtained using our active sampling approach. If we use, for example, surrogate decision tree, complexity can be measured using the average path length, and we compare it to the complexity of a reference model. The reference model in our case is the model obtained after adding all the samples belonging to the A to train the surrogate model simply using passive sampling. We evaluated the approximation quality of our method using 10 benchmark datasets ranging from classification to regression tests with 3 types of black box model, namely random forest, support vector machine, and the multi-layer perceptor. For the evaluation of the quality of the approximation, we used the area under curve for classification task and the root mean square error for regression. We computed also the statistical significance of the result by computing the mean and the losses based on the Bayesian correlated t-test with the null hypothesis that a given baseline wins against our approach. We used decision tree as a surrogate model, and we compared our surrogate decision tree to several baselines. TD is a surrogate decision tree trained on DGD with reference to dependent, as DG is used to train the black box model G. TID, the surrogate decision tree trained on DSID with reference to independent, as DS is an independent dataset of the training of G. TR, the surrogate decision tree trained using a random sampling from GA. TP, surrogate decision tree trained using all the samples from GA. P with reference to passive sampling, and TAL, it is a surrogate decision tree obtained using ASIM. This is an overview of the detailed predictive performance results comparing our decision tree to the remaining baseline, absolute with reference to the performance in approximating the real data, and relative with the reference to the performance in approximating the black box model G, you can see that our method achieved higher ROC than the remaining method in terms of absolute and relative performance and a lower root mean square error for regression task. We have also computed the average rank achieved by each model. Rank 1 means that the model was the best performing on all the data sets and all the tasks. Lower rank is always better, of course. Our method has a lower, which is very close to the black box model for the absolute performance and has the lowest rank in terms of the relative performance compared to the remaining trees. The remaining trees also have a higher number of significant losses against our tree. We also suggested to compare the complexity of the different surrogate decision tree. This is our surrogate decision tree. This is the tree used as a reference model. You can see that we have either a lower or a similar rank, and this is stated by our selection criteria. In some of the cases, we slightly exceeded this rank, since in the last iteration, the last added sample resulted in exceeding the complexity of the reference model, and from that sample we stop iterating, for example in the 6th and the 9th cases. You can see also that the independent tree has a lower rank, and this is explained by the fact that it has the least amount of data point, so it has a lower number of rules to learn. However, this tree cannot generalize very well, even in terms of approximating the black box model, and that's why TP obtained using passive sampling was used as a reference model in our case. Now I would like to show you some aspects of model debugging and interpretation using surrogate decision tree. First aspect is invalid feature detection. Invalid feature here are meant the features that are highly correlated with the response variable. Of course, they make the prediction task more easier. However, they omit the influence of the remaining attributes that may be useful to understand more aspects about the data. If we consider the student grade data set, the response variable, the grade in the final class, is highly correlated with the previous grades. That's why we find those features in the top branching of all the trees, if not in all the splitting nodes, omitting thus the influence of the remaining features such as social, demographic, and school-related features which not desired. Also, they allow surrogate decision tree allow for block box models comparison. For this dataset, SVM outperforms random forest, and while investigating the surrogate decision tree, we found that this is highly correlated with the presence of skin thickness in the top branching of the poor performing model. It also highlights the importance of the glucose feature. That's why we find it in the top branching of all the features, and for the highly performing one, the range of the value of this feature is lower than the poorly performing one. The third aspect is with regard to fairness evaluation, where we want to use the decision tree to detect whether the decision of the black box model is influenced by some of the prejudiced features that are in the data set. For the case of the student grade, we want to predict the grade of the students, and the label feature is considered as the sensitive information. We start by estimating the overall effect of changing the gender label on the output of the black box model by measuring this quantity. We also estimate the dependence of the surrogate decision tree on the gender by measuring the deviation in the output of the black box model given different gender information by considering the subtrees branching on the gender feature. And finally, we measure the fraction of the overall dependence of the black box model on gender that is accounted for the subtrees routing at n by this proportion. For the surrogate decision tree is highly dependent on the gender information. Delta n is ranging between 0.57 and 0.69, and the proportion of the student P is estimated to be between 34% and 38%, and the estimated fraction of the overall dependence is between 65% and 68%. After identifying these subgroups that seem to be adversely affected by the gender information, we may train another machine learning model to generate more reliable prediction for these subgroups. In the end, we have proposed an active sampling method for learning interpretable surrogate machine learning models that establish a trade-off between complexity and accuracy. It is flexible for learning different types of interpretable and black box model for supervised learning tasks. Thank you for your attention. Our work is supported by the DFE within the Collaborative Research Center SFB 876 and the Federal Ministry of Education and Research of Germany as part of the Competence Center for Machine Learning Amal 2R. Thank you.